Okay, hi everyone. In this presentation, I'm just going to be showing you what I worked on, what I learned throughout my internship here at Active Design Group. In the first week, I began to learn how to use Grasshopper and Rhino. And at the start, I was kind of familiar with Rhino, but I never really learned how to use Grasshopper. So Mr. Shim told me to start with try modeling real-world structures. So this was a canopy near the office outside. Took a picture of it, and I tried to model the basic form of it inside Grasshopper. After that, I tried modeling the One World Trade Center, which was a much more bigger but more realistic structure. And afterwards, I modeled more complex forms, more geometries, such as this wormhole, hyperbolic paraboloid, and these Voronoi tessellated objects. This really taught me how I could convert geometric parameters into parametric logic and constraints, as well as learning how useful Grasshopper is in creating more complex geometries that would be pretty difficult to model by hand. Next, I learned how to import all this into more finite element analysis software, such as SAP and ETABS. One of the things I made was a geodesic dome. Using Python plugin, I was able to create a geodesic dome that can vary the number of frequencies and subdivisions within it. And after importing into ETABS or SAP, and I was able to see the stress distribution. And another thing I made was a Voronoi roof pattern. After modeling it in Rhino and ETAB, or Rhino and Grasshopper, I applied the constraints and shell elements onto the roof element. And I was able to observe the axial forces distributed across. Next, I was able to create a twisting high-rise, and that could vary the number of floors, the number of heights, the height and the radius, as well as the degree at which it turns. And importing that into SAP or ETABS and seeing the axial deformation and the stress distribution across the axial members. The next thing I modeled was a parametric truss. These were more structurally realistic models. After making them, I imported them all into SAP 2000, and I learned how to use load combinations, applying them, and being able to read the force diagrams for each dead load, live load, and wind loads. The next thing I learned was with composite beam designs in ETABS. I learned how to create frame sections, creating the deck sections, assigning the deck, load combinations, assigning those, and then observing the deformation and axial forces and moment forces. The one thing Mr. Shim was very adamant on was me being able to compare ETABS values with hand-calculated values. So I took a lot of pictures of my hand calculations, and I compared them with the ETABS values, with the max moments occurring at the beams and girders. This was a much more bigger composite beam design setup. I learned how to iteratively analyze the different members and determine assigning the different members restraints and the different number of shear studs. Same thing with more complex geometries with triangle-based structures and rhombus. This was lateral load ETABS analysis Mr. Shim provided me to study moment and coupling beams. I observed the axial forces, shear forces, and moments, and I also did the same thing, calculated the moments and coupling moments, compared them with ETABS, and observed the differences that occur. This was a self-study model. I modeled it was only 15 stories, and I assigned the piers and added the labels to be able to analyze the effect of the lateral reinforcement that coupling moments or the link beams can provide. And same thing, I calculated the coupling moments and total moments and compared with the ETABS values with mine. In my second self-study, I studied lateral loads and the effects of lateral connections. So the effect of cross-bracing, lateral bracing, and V-bracing, how those each individually influence the overall reactions between the towers, seeing how the differences can be pretty noticeable, as well as calculating the moments and axial forces, same thing, calculating or comparing with ETABS. For my third self-study, I moved on to like 3D simpler structures. It's just a basic frame structure with 4 beams, 4 columns, and through an iterative comparison, I looked at the effects of changing the slabs, changing the decks, changing the connections, pin for moment, and stuff like that, observing how axial moments and stress distributions are affected when changing those values. These are all the studies I did, looking at the bending, moments, and deformations. A big part of this internship was going to the NJIT makerspace, and over there was a laser cutter, and this was the first thing we made, which was geodesic dome, which is what we made in the beginning, first week. The thing with laser cutting is you need to be very careful with the connections, because the kerf of the laser, you need to consider that when modeling your designs. So, although this one, sorry.
Tolerance, you mean?
Yeah, the tolerance, yeah. The tolerances, but also the kerf of the laser. So that's 2 things you need to account for. And although this one came out pretty well, there was still a little minute gap in between the connections. So we took that into account for future.
So is there an actual angle in the cut in the node to make sure you get the dome shape?
Yeah, so these braces, they're curved by I think 5 degrees, and the connections for each one, you have to account for the curve as well.
Okay.
So it came out pretty well. Now this was another small project we did with the James Webb Space Telescope. It started off with just like a table stand, but Mr. Shim suggested we make it into like a clock. So we got these clock mechanisms from Amazon. And I took the dimensions, considered the size of it, and the weight of it as well. So I made some changes to the design to account for all that. And it came out pretty well. This is the laser cutting. Yeah. Mr. Shim provided me sticks, so I made this tensegrity model with dowels. And I wanted to connect that with laser cutting. So I modeled an icosahedron in Rhino and laid it out into a spreadsheet, and we ended up laser cutting it, and then it came out pretty well. We're small though. One of the big projects we did was a moon base layout, or laser cut. This was a Martian habitat created by AI Space Factory for the NASA competition for moon base pitching. This was the first place winner they got, and this was.
Is this yours?
No. This was. This was it was like a 3D printed concrete. They didn't use concrete, but they used what is it? Soil. I think soil, but also more silicon-based material, and they used that as a 3D printer. But I just wanted to study the structural makeup of it, so I modeled in Rhino the structure, just the basic outline of the Marshall base, and I created a couple iterative designs, and then assembled it to fit in joinery, and then laid it all out into a laser cutting template, and it came out pretty well. And after that, I wanted to see more of the structural differences that can occur when maybe varying the outside frame of it. So I changed up the different domes into digrid, grid, raised grid, and hexagonal. And with the structural analysis, I observed how the axial forces reacted and the stress distribution between all the designs.
So which is the most efficient one?
This one. Oh, this one. I think it makes sense because it provides a lot of lateral bracing compared to this, just the grid bracing. And although it uses a lot more material, it distributes the stress pretty well, evenly.
And the lightest is the hexagon?
Yes, I believe so.
The one right.
And this was a buckling and lateral load analysis, observing how 10 kips of force, because on Mars there's pretty considerable wind. So this was simple design. And this was another model for a new dome I made. This one I modeled into Rhino. This is different geometry. And I put it out into a spreadsheet, accounted for, because the angle was different for every connection. I had to label all of them, calculate all the angles, and order them from largest to smallest. And then I put them all in the spreadsheet, minimized the amount of wasted space. And after organizing all the pieces, I layered it all out, and this was the final assembled dome, which came out pretty well. Another structural analysis, observing the deformation, axial forces, and stress contours. And because this one is more akin to moon-based designs. So on the moon, you would have to, well, I guess Mars too, but for the moon, you'd have to obviously pressurize the inside in order for humans to live inside. NASA suggests, I think, 0.7 atmospheres of pressure within for safety. And I put shell elements across every triangle and assigned 0.0102 kips per square inch loading on each of the shell elements to simulate the expansive force. And you can see the deformation and a lot of the axial forces and stresses occurring across the members. One of my personal projects I wanted to work on was try and model my own high-rise structure. And looking at a lot of the structures, I kind of found more inspiration in these buildings and their core structures. And it inspired me to just practice my sketching, being able to draw my own architectural designs. And I tried to come up with my own brace core structures, and then using Rhino to experiment with the models, experiment with the designs and how it would look. And one of my favorite parts of this internship was going on site visits. I got to see a lot of the structural foundation building, as well as how different buildings have their beams and girders made up, how difficult it is to really observe exactly what the structural makeup is, since there's a lot of stuff in the way. And this was one of the Hotel Riviera site visits we went recently, and it was pretty interesting. And during the 5th or 6th week, we went to Orlando, Florida to attend the UKC 2026, it's like a technical conference with a lot of Korean Americans around the world. And they all came together to showcase their own research and their work they did. And one of my favorite parts was going to their poster sessions, which included a lot of PhD students showcasing their individual research in their fields. And it really inspired me and really showed me how important research is and what the possibilities are. I want to thank everybody here for listening, and Mr. Shim for teaching me so much, and thank you so much.